want to talk to you about average atomic mass. Average atomic mass, when you look at the periodic table, you'll see the atomic mass listed on the table. So when we look at the table and we see hydrogen 1.008, lithium 6.94, beryllium 9.01, that is the atomic mass of the element. What does that represent? Well, the atomic mass represents a weighted average of all the naturally occurring isotopes of an element. So when you have an element, for example, when you have iron, you may have some isotope iron 55 and some isotope iron 56, and this number represents an average of those isotopes. But it's not just a numeric average, it's a weighted average. The reason why we have a weighted average is because a numeric average just wouldn't make sense. It wouldn't take into account that maybe one isotope is more common than another isotope. So, for example, so what does that mean? Hydrogen has 3 isotopes. Now, hydrogen's 3 isotopes are hydrogen 1, hydrogen 2, and hydrogen 3. So let me just write those down. Now, you've learned already that this top number is the mass number, and that's the number of protons and neutrons in the isotope. And the bottom number is the atomic number. That's the number of protons. That stays the same. So when we talk about the mass of hydrogen, it would be silly to take a numeric average. The numeric average of 1, 2, and 3 would be 2. So a numeric average would be like, we got some hydrogen 1, we've got some hydrogen 2, we've got some hydrogen 3, 3 different isotopes divided by 3, we get 6 divided by 3, which is 2, and that would make no sense. The reason why it would make no sense is that when we look at hydrogen, these 3 isotopes of hydrogen, we find out that this is hydrogen 1 is by far the most common. Which means that when you if you have a bunch of hydrogen atoms, almost all of them are going to be hydrogen 1. So the average really should be close to 1 and not halfway between 1 and 3. Almost all hydrogen atoms that you find in the water that you drink, in the molecules that you have in your body, chances are if you find a hydrogen atom, it is a hydrogen 1. So the average should be really take into account how common each of these are. So what we do is we take a weighted average. So the atomic mass, and you can see on the periodic table that if you look at hydrogen, its atomic mass is close to 1. It's 1.008. That indicates just that hydrogen 1 is much, much more common than hydrogen 2 or 3. So how do you take the weighted average? Well, let's go back and look at our hydrogen example. So here's hydrogen's naturally occurring isotopes. You can see that hydrogen 1 is 99.9816% of all hydrogen atoms are hydrogen 1, and that only 0.01% is hydrogen 2, and almost none are hydrogen 3. So we're not even going to count those into the average because they don't contribute much to the average because almost no hydrogen atoms are hydrogen 3. You can see that the mass is not exactly 1. See, the mass number is 1, but the atomic mass of the isotope is not exactly 1. And the reason why is each isotope's mass is measured relative to carbon-12 being 12 exactly. And carbon-12 has 6 protons and 6 neutrons. So it's kind of the average mass of 6 protons and 6 neutrons. And so these come out very close to whole numbers, but they're not exactly whole numbers. Okay? So when we take the average, in order to take this weighted average, what we do is we multiply the abundance by the mass. We take the percentage, but we write it as a decimal, and then we multiply it by the mass, and we'll do that for each isotope and add them. So the atomic mass of hydrogen is going to equal the abundance of hydrogen 1, which is 0.999816 times 1.007825, okay, AMU, plus 0.000115 times 2.014101 AMU. And when we do those two multiplications, okay, I'm going to do those on my calculator right now. 0.999816 plus or times 1.007825 equals, and then I'm going to add that to 0.000115 times 2.014101, and I get 1.00787 AMU. Remember, the symbol for U is AMU, which is, for all practical purposes, the number on the periodic table, 1.008. You can see that our answer was pretty much 1.008. So that's where the number on the periodic table comes from. It represents an average, which is why when you do calculations, you have to use the mass on the periodic table unless you have a pure isotope that's all alone. But in nature, you have a mixture of all the isotopes, and that number on the table is the average mass of that mixture.